The Arduino Uno is a very popular microcontroller amongst hobbyists today. The reason for this is that it's really easy to get started with Arduino. There's tons of YouTube videos and resources online, and there's a lot of community help when getting started with the Arduino. But the Atmega 328 8-bit processor is very limited by today's standards, and it makes more sense to get acquainted with a processor such as the LPC802. The LPC802 is a 32-bit ARM M0 Plus processor. The purpose of this project was to use the LPC802 development board to create a vertical farm element. Vertical farming is the practice of growing crops indoors as opposed to growing them outdoors in large farm fields. It's called vertical farming because modules just like this one are stacked on top of each other. This is a very simplified version of a vertical farm as there's no temperature or humidity control. But what this system does is it automatically cycles an LED grow light on and off at time intervals that are pre-programmed into the LPC802 board. This display here shows the amount of time until the light switches. So right now this means that there's 15 hours and 57 minutes until the light is to change. So here's a demonstration of the light timer functioning. So right now, as you can see, that's going to count down. And when it reaches 0, the light's going to turn off. Now it's updated with the time until it turns back on. Right now the device is set to do a 16-hour on, 8-hour off light cycle. If I want to switch it to a 12-hour on, 12-hour off light cycle, then all I have to do is flick this interrupt enable switch right here, and it switches to a 12-hour cycle. If we were to wait 12 hours, the light would turn off, the display would get reloaded with 11:59, and then the light would stay off for 12 more hours, at which point it would cycle again. The other main function that this device performs is automated watering of the plants. So down here you can see there's a sensor wire that goes to the ADC, and right here there's a small pump, and here's it's called a halo dripper, I believe. This was 3D printed in the second floor of the Bergeron Center. So what you'll see is that when I remove the sensor wire, the pump will turn on. I'm going to demo our sensor working on this dry soil. So here I'm going to grab the sensor, insert it into the dry soil, and as we can see, the pump would be on. And let me just water this plant here. I might make a little mess, but that's okay. I'll clean up after. So I'll water it, and as you can see, the pump is turned off now that we've watered it. Originally, I had planned on using these capacitive soil moisture sensors to measure the soil moisture level. The reason I was going to use these over the conductive ones is because I didn't want the sensor to destroy itself over time through conduction. That's why I chose the capacitive one. Another reason is because the capacitive one uses the ADC, meanwhile the conductive sensors just send out a TTL signal. Now, what I've done as a fallback plan is it's not exactly falling back to the conductive sensor because it doesn't send out a TTL signal. Instead, what I've done is I've created my own conductive sensor just by using 2 stripped pieces of wire, and this value goes to the ADC. And the reason it's not a big deal is because when I have to replace these wires, all I have to do is cut the corroded part off and strip more wire off. I don't have to buy any new sensor. The second switch on this device tells the display to display the ADC value as opposed to the time remaining. Right now, inside of our soil, we're measuring 1780 for our conductivity. If I am to remove this wire and hold it in the air, we could see that the ADC is measuring full saturation of 4096. If I dip this wire in the water, the ADC is measuring a value near 1000. And if I short these wires together, the ADC measures almost 0. When designing an embedded system, it's helpful to create a hardware architecture where you can clearly see what your inputs and outputs are. Here's the hardware architecture diagram of this vertical farm. So we have the grow light and the pump and the display module as our 3 outputs, and our inputs are the sensor, the 2 toggle switches, and the power. This vertical farm consists of a LED strip power supply and a power module that is made out of 2 different DC to DC converters. 12-volt power supply takes 120 volts AC and converts it to a safe 12 volts DC for the project. The power module has two buck and boost modules. One steps the 12 up to 30 for the grow light, and the other one steps the 12 down to 5 to power the LPC802, the mini pump, and the relay coils. The LPC802 has its own power system that regulates this 5 volts down to the 3.3 volt logic required by the processor itself, and that power is used to power the display module and the sensor. In this schematic diagram, we could see the layout of the components for this system. Here we have the LPC802 development board. Here's the analog mux. Here's the digital display. Here's the 2 relay module. Here's the grow light. Here's the pump. This sensor was omitted because its values were not properly being read, but the wiring is the same if you omit VCC. The power system consists of the 12-volt DC power supply and the 2 buck and boost converter modules. The 2 input switches are connected to a 10K pull-up resistor to the 3.3 volts. As you can see, I chose to use a Tupperware container as an enclosure for my project. Here you could see the LPC802 and an interface board that I made to make removal of the LPC802 easier and quicker. This is the 12-volt power supply intended for LED strips. That connects to the power module through one of these connectors. The power module has a step-up converter, which is the top one, and a step-down converter, which is the bottom one. This wire here goes to the relay that controls the light, and this orange wire here is what sends power down to the pump through this wire here. This wire here, this is for the sensor, so that is the 3 wires shown right here, capacitive soil moisture sensor. The display just consists of the analog mux and the 7-segment display and the interface cable that I made to make wiring easier. This board was made so that I could remove the LPC802 easily from my system without having to repeat wiring. As you can see, all the wires are soldered directly onto here, and I know the wiring is correct on this top board, so all I have to do is remove this board to remove the LPC802. The LPC802 receives power from the power module through this USB cable that has been cut and the data lines removed. This software architecture diagram describes the code that is used to drive this vertical farm. So the SysTick timer is used to keep track of time in seconds. When 8 hours has passed, or 12 hours, or whatever on time it is, it sends a interrupt to the light handler to toggle the light. The state of the toggle switch is used to reload what value for on time should be used in SysTick. The WKT timer multiplexes through the different segments on the 7-segment display to make it appear as if all the digits are on at the same time. In reality, every time wake up timer is called, it flashes through 1 digit. This is set to happen at 100 kilohertz. The toggle switch is used to determine if the ADC or the time remaining should be displayed. Finally, in the main loop, I pull the ADC, and the ADC is measuring the soil moisture. If the soil moisture falls below a threshold value determined through experiment, then it sets the relay GPIO for the pump.